Hello class, welcome back. We're going to pick up our lectures today starting with Europe in the early 19th century. What we're looking at here in the red outline is Napoleon's French Empire. So you can see it's quite large, it's encompassed most of Europe. Now, Napoleon wants to take over all of Europe, but he can't invade England because they have a very strong navy. And the problem is that Russia is trading with England, which is diminishing the French influence throughout the continental Europe. And so in 1812, Napoleon decides to invade Russia under the excuse that it's to free Poland. So here it is, a figure that shows Napoleon's invasion of Russia in 1812. And this is one of the most famous scientific visualizations, by the way. So if you want to be an aficionado of scientific visualizations, this is a good one to know. This line width represents the size of Napoleon's army. And this is Moscow. And so what we can see here is that as Napoleon marches into Russia, the width of the line becomes narrower and narrower. And by the time he reaches Moscow, it's diminished a lot. And on his way back, it gets even narrower and narrower. And in fact, what I have here on the bottom is a thermometer scale. And so here's Celsius, 0, -13, -25, -38. And it shows what the temperatures are at various dates along Napoleon's retreat. And so you can see that he had a very unsuccessful campaign in Russia. He crossed the Niemen River with 600,000 men, and he returned 6 months later with 10,000 men. Very devastating campaign. And so here's a painting of their retreat. Very unpleasant. One of the things that is very noteworthy about this campaign was that Napoleon's army at the time was very fashionable in having these buttons. These are buttons made out of tin. And when tin is put in extreme cold, it has a very fascinating phase transition. Okay, so here's a phase transition of tin.
At our temperature, tin is a nice, shiny metal. However, when tin experiences temperatures that are lower than 56 degrees Fahrenheit or 13 degrees Celsius, tin turns to dust. So legend has it.
Oh my God, what a fantastic phase transition. Let's watch that one more time.
Tin is a nice, shiny metal. However, when tin experiences temperatures that are lower than 56 degrees Fahrenheit or 13 degrees Celsius, tin turns to dust.
Wow.
So legend has it.
All right. So at high temperature, tin exists in this structure, which is the beta state of tin. It's called white tin. And at low temperatures, there's this phase transition to gray tin, which is in the diamond structure. This phase transition's equilibrium temperature is actually 13 degrees Celsius, but it doesn't start until -15 degrees Celsius. And if this was in class, I would ask you why, but since this is an online asynchronous lecture, the reason is because you have to go to some significant values lower. Remember in the metastability lecture, you have to go to significant supercooling before the transition actually can overcome the nucleation barrier. Anyway, so out of these two phases, which phase has higher entropy? You guys should be very good at this by now. The high temperature phase has higher entropy, right? It's the extensive advantage. But another interesting question is why? You know, looking at these two crystal structures, can you rationalize why this phase has higher entropy than this phase? It's not so straightforward, right? And so this is the topic of today's lecture. This is lecture 18, Vibrational Entropy of Solids. And what we're going to talk about today is lattice vibrations, entropy, and heat capacity. It's not just something that we're doing for material science and engineering. Historically, this is also one of the most important pieces of evidence for quantum mechanics. So what we're going to do today is we're going to derive the heat capacity of solids using increasingly sophisticated physics and statistical mechanics. And then I'm going to conclude the lecture with a little description of how phonons are measured and calculated today. Okay, so let's get started. The first thing that I want to show you is a graph of the heat capacity of solids. And this is a variety of solids. And here is the frequency of occurrence as a function of the heat capacity. And so this is like joules per mole Kelvin, I'm guessing. So if I look over here, the heat capacity of aluminum, antimony, copper, gold, silver, these are all about 3R. And diamond is a little bit of an outlier at 0.735R. So why are all solids, regardless of chemical composition, why are they all having a 3R heat capacity around room temperature? Well, remember previously at the end of last lecture, I described how each degree of freedom essentially affords a material 1/2 kBt in the heat capacity. So a monatomic gas has 3 degrees of freedom, right? Translational X, Y, Z. So you get 3/2 kBt. What about a solid? How many should a solid have? Well, you can already kind of figure it out since it's 3R, so it has 6 degrees of freedom. The 6 degrees of freedom in a solid is it can have position. So position, it gives you 3 degrees of freedom, and then the momentum also gives you 3 more degrees of freedom. So you have 6 degrees of freedom for each atom on a lattice site, and so that gives you a total heat capacity of 3R. This is a very important law. It's called the law of Dulong Petit. This was an empirical law, which means that people knew this experimentally before they understood it, but most solids have a heat capacity of 3R under ambient conditions. Now diamond is the outlier, right? So if you actually plot the heat capacity as a function of temperature, it looks something like this. So at room temperature, around 300 Kelvin, most solids have heat capacities around 3R. But actually, when you go to very low temperatures, the heat capacities of nearly all materials go to 0. And so carbon, on the other hand, has a very low heat capacity at room temperature. But if you go to much higher temperature, diamond will eventually approach 3R for the heat capacity. How can we rationalize this from statistical mechanics? Well, so at the last lecture, the end of the last lecture, we were talking about the heat capacity of a diatomic gas, right? And I showed this figure, and we were saying how when you increase the temperature, you are increasing the heat capacity of a diatomic gas, or conversely, when you decrease the temperature, you reduce the heat capacity of a diatomic gas, right? And we described how the reason why a diatomic molecule can store more heat as you increase the temperature is that when you increase the temperature, you activate new degrees of freedom, right? So at low temperature, you only have translational degrees of freedom. At intermediate temperatures, you can have your diatomic molecule start rotating, and so that's another way you can store energy in the molecule. And when you go to very, very high temperatures, you can access higher vibrational modes than just the 0-point energy vibration. So in diatomic gases, the heat capacity decreases with temperature because we are freezing out degrees of freedom in the diatomic molecule, right? When I go to lower temperature, I no longer access vibrational modes, or I no longer access rotational modes, and finally I'm only stuck with translational modes. So can we rationalize this observation also from an idea of freezing out degrees of freedom? Can we use that to explain the heat capacity of solids? So yes, that's why I posed the question. Albert Einstein derived a model for atoms vibrating on a lattice, and he came up with this assumption. He said, assume atoms vibrate on a crystal lattice in a harmonic potential, but can only vibrate at a single frequency. Okay, and so the idea is that at low temperatures, some fraction of the atoms are vibrating and the others are frozen out, so they're no longer vibrating. This is easy for you to write in your notes, but actually this is a tremendous leap of intellectual physical insight, right? How can you just assume that atoms are vibrating at a single frequency? That's such a strange thing for someone to say, especially back in 1905. So let me rationalize Einstein's assumption with a little bit of historical context. So the law of Dulong Petit was formulated in 1819. That's the Cp equals 3R for solids. And Einstein proposed his model for solids in 1907 in this paper titled Planck's Theory of Radiation, the Theory of Specific Heat. In between this time, in 1896, Boltzmann's work on statistical mechanics is happening. And in 1905 is Einstein's very famous year called his Annus Mirabilis, miracle year. He publishes 4 papers that fundamentally change modern physics. And the most important from our perspective right now is concerning a heuristic point of view towards the emission and transformation of light. And in this work, Einstein uses Boltzmann's theories from statistical mechanics to derive some really fundamental insights into quantum mechanics. And it's a little bit unfortunate, it's very unfortunate, because Einstein published this in 1905, but Boltzmann was actually so depressed that nobody was acknowledging or using statistical mechanics, and he was receiving so much backlash against this that he actually committed suicide in 1906. And so if he had just lived a little longer, he would have seen some really spectacular work coming out of Einstein using his statistical mechanical principles. So you're all grad students, and you're all training to become scientists and to enter the scientific enterprise. If you're trained to be a scientist, there is no one better to read than Einstein. His papers are beautiful, and actually today I'm going to devote a pretty significant part of our lecture to read this particular paper, at least the introduction, okay? And so for those of you who are not familiar with this paper, this is the one that won him the Nobel Prize eventually and is regarding the photoelectric effect. So just to remind you, the photoelectric effect is this observation that when you have an alkali metal like potassium, if you shine different wavelengths of light on the metal, under some conditions you will eject electrons. If the light is red, then you will not eject any electrons. But once you get to certain colors like green or blue, you'll eject electrons, and you'll eject electrons with a kinetic energy that is proportional to the energy of that light, where the energy of a light packet is E equals h, which is Planck's constant times nu, which is the frequency, right? And as we know from quantum mechanics, the energies that are available to light is quantized. But again, they didn't know that before Einstein wrote this paper. So let's read Einstein's paper to see how he came to this conclusion. All right, here we go. A profound formal distinction exists between the theoretical concepts which physicists have formed regarding gases and other ponderable bodies and the Maxwellian theory of electromagnetic processes in so-called empty space. Okay, a profound formal distinction exists between gases and Maxwell's wave theory. Okay, so I'm just going to annotate this on the side. Particle and waves are fundamentally different. While we consider the state of a body to be completely determined by the positions and velocities of a very large yet finite number of atoms and electrons, we make use of continuous spatial functions to describe the electromagnetic state of a given volume, and a finite number of parameters cannot be regarded as sufficient for the complete determination of such a state. Okay, what's he saying here? Basically, particles are made up of a very large but finite number of atoms that are indivisible, where on the other hand, waves are continuous spatial functions like sines or cosines, right? According to the Maxwellian theory, energy is to be considered a continuous spatial function in the case of all purely electromagnetic phenomena, including light, while the energy of a ponderable object, like atoms or electrons, should, according to the present conceptions of physicists, be represented as a sum carried over the atoms and electrons. Okay? The energy of a ponderable body can be subdivided into the energy of a ponderable body cannot be subdivided into arbitrarily many or arbitrarily small parts, while the energy of a beam of light from a point source, according to Maxwell's theory, is continuously spread over an ever-increasing volume. So the energy spectrum of waves is continuous, like sines and cosines, right? I can go, arbitrarily small in terms of the possibilities in discretizing the waves, but I cannot divide atoms indefinitely, right? And I also cannot divide their energy indefinitely. And so if I'm looking at a point source, these are fundamentally different descriptions, right? One is a wave description, and one of these would be particles. So there is a profound formal distinction between these two. The wave theory of light, which operates with continuous spatial functions, has worked well in the representation of purely optical phenomena and will probably never be replaced by another theory. It should be kept in mind, however, that the optical observations refer to time averages rather than their instantaneous values. Okay, time averages rather than instantaneous values. This is some statistical mechanics language. In spite of the complete experimental confirmation of the theory, as applied to diffraction, reflection, refraction, dispersion, etc., it is still conceivable that the theory of light, which operates with continuous spatial functions, may lead to contradictions with experience when it is applied to the phenomena of the emission and transformation of light. Okay, so here we had some language that we can start to see some statistical mechanics language, and here, what a bold statement, right? Spatial functions may lead to contradictions with emission and transformation of light, and that's the topic of this paper, right? The emission and transformation of light. It seems to me that the observations associated with blackbody radiation, fluorescence, the production of cathode rays by ultraviolet light, and other related phenomena is connected with the emission or transformation of light are more readily understood if one assumes that the energy of light is discontinuously distributed through space. In accordance with the assumption to be considered here, the energy of a light ray spreading out from a point source is not continuously distributed over an increasing space, but consists of a finite number of energy quanta which are localized at points in space, which move without dividing, and which can only be produced and absorbed as complete units. In the following, I wish to present the line of thought and the facts which have led me to this point of view, hoping that this approach may be useful to some investigators in their research. Wow. So just to remind you, Einstein is 26 years old when he wrote this section. Look how bold this is, okay? You know, in accordance to the assumption to be considered here, you know, the energy of a light ray spreading from a point is not continuously distributed, but consists of a finite number of energy quanta. And this is the first time the word energy quanta appears in the scientific literature. Right, so anyway, the rest of this paper is actually not so rigorous, right? That's why it's called a heuristic point of view. The rest of the paper, what he does is he takes the entropy of radiation from Planck's law, and he shows that it looks a lot like the entropy of gas molecules from Boltzmann statistics. And so the conclusion here is that because gas molecules are so-called ponderable objects, they're indivisible, he's conjecturing that radiation, which is light, may also be composed of indivisible ponderable objects, which is, you know, what we now know today as photons, right? And so anyway, this is, if you want to read through the rest of the paper, it's a wonderful paper. And at the end of the paper, Einstein makes a very bold prediction, which is that the kinetic energy of an electron is the incoming photon's energy, h nu, minus something called the work function, which is how much energy it takes to extract an electron from a particular metal. Okay, so if we go back to history, Einstein wrote this paper in 1905, and he's still thinking about quantum mechanics when he writes this paper in 1907. But in 1914, Millikan at Caltech demonstrates, he was actually trying to prove Einstein's this paper wrong. He was trying to prove that this prediction was not the case, but in fact he ends up confirming Einstein's prediction. He does the photoelectric experiment and demonstrates that indeed the kinetic energy of the electron is equal to h nu minus the work function. In 1919, in this meantime, Einstein's also working on general relativity. So Sir Arthur Eddington from England, he quote-unquote measures general relativity. He does this solar eclipse, and he measures the light bending from the sun around the moon. It turns out that his error bars are actually too big to make a real rigorous conclusion, but he publishes the result anyway, saying that Einstein was correct. This is, 1919. This is following World War I. So Sir Arthur Eddington is trying to repair scientific community with Germany. So he says that this is correct, and later it is indeed confirmed that the predictions were true. Right, more careful measurements do show that general relativity was correct. And anyway, after all this, Einstein wins the Nobel Prize in 1921, and he wins the Nobel Prize for this paper, for considering the heuristic point of view towards the emission and transformation of light. Not for relativity, actually. And finally, in 1927, this is what's called the Fifth Solvay Conference, and this is the birth of quantum mechanics. And so this is really a who's who of quantum mechanics. We have here Planck, Bohr, Heisenberg, Madame Curie, it's hard to say, De Broglie, Compton, Einstein, Schrödinger, Born, Dirac, Fermi, von Neumann, Pauli, von Lau, Hilbert, Wien, Bose, Summerfield. All the big names are here, and this is when quantum mechanics is really getting started. But again, it all got started because of Einstein's 1905 paper. So why did I just do all this? Why did I talk about all this history? It's because in this Einstein model from 1907, if you just write down in your notes that assume atoms vibrate on a crystal lattice in a harmonic potential, but can only vibrate at a single frequency, that's an immensely unsatisfying assumption, right? It's such a crazy assumption that atoms can only vibrate at a single frequency. What? Why would he say that? Why would Einstein make such an assumption? And as you can see, it comes from this idea that energy is quantized. Okay, so we're doing Einstein's model of heat capacity. All right, so Einstein's describing a lattice that looks kind of like this, right? So we have some atom, and the atom is vibrating back and forth between these two other atoms in this lattice. And if I were to draw the energy as a function of position, you would have what we call a harmonic potential, right? And in a harmonic potential, right, we're vibrating back and forth in this parabolic energy well. From quantum mechanics, we know that the energy eigenvalues of the harmonic potential is actually not continuous, but has discrete energy levels. So here we have the energies are equal to n plus 1/2 h nu, where n equals 0, 1, 2, 3, etc. Okay. Remember, if you haven't taken quantum mechanics, this is just the energy eigenvalue that comes out for these particular solutions of the Schrödinger equation, where these quantum numbers represent the state that is the vibrational state that's being activated. Okay, so let's take this energy and plug it into a partition function. So we're going to say the partition function for vibrational modes is equal to sum over n. So n is which state I have. What are we going to write here? Just very simply, exp negative beta e sub n, right? So I plug e sub n into here, and what do I get? I get equals e to the negative beta h nu over 2 times sum over n to infinity e to the negative beta h nu over, e to the negative beta h nu n. How do we get this? Remember, so I just, I kind of separated, so this 1/2 h nu part comes out here, right? E to the negative beta times 1/2 h nu, that can be separated from the rest of the exponential. And for the part that includes nh nu, I just have e to the negative beta h nu n, which is summed, okay? So this expression right here, the summation of a negative exponential, is also can be written as what we call a geometric series. And in a geometric series, we have here that sum over n to infinity of x to the n equals 1 over 1 minus x. Okay, so what we're going to do here is we're going to treat x equals e to the negative beta h nu, and we're going to plug this into this. So I'm going to go to a new page. So q, I'm just going to rewrite it really fast so that you have this on your notes, equals exp negative beta h nu over 2 times the sum into infinity exp negative beta h nu n. So this, once we plugged in the geometric series, we can now rewrite this as exp negative beta h nu over 2 times 1 minus exp negative beta h nu. Okay? Because I'm taking this term from here, and this term, I'm going over here, I'm turning it into 1 over 1 minus x, and I'm treating x as e to the negative beta h nu. So that's this expression down here. We're going to create a new variable, which we're going to call theta. We're just doing this for convenience. I'll tell you what this means later. Which is going to be h nu divided by Boltzmann's constant. Okay, and so this is now going to be written as e to the negative theta over 2t divided by 1 minus e to the negative theta over t. Okay, do you see how that transformation happens? Okay. Oops. So this is the partition function for the Einstein model. So this is for a single atom vibrating on a lattice. What do we do for the whole lattice? Well, we would have big Q equals Q to the n. Do we divide through by n factorial? No, we don't, right? Why not? Because these are distinguishable sites, right? We only divide through if the particles are indistinguishable. When you have them on a lattice site, they're distinguishable. Okay, so do not divide by n factorial because particles are distinguishable. All right, so let's go to this expression. So in 3 dimensions, so now we have atoms that can vibrate up, down, left, and right, right? So this way, and this way. So what we're going to do now is we're going to say the total partition function, Q, is equal to the small q, which was e to the negative theta over 2t, divided by 1 minus e to the negative theta over t. We're now going to take it to the 3n power, okay? So n because we have n sites, and 3 because we have 3 spatial dimensions to vibrate on. So remember, we're trying to solve for the heat capacity of a solid, and so the heat capacity is equal to partial E partial T, where E is the average energy of the system, which is equal to partial log Q partial beta. This equals to kBT squared partial log Q partial T. If you don't remember how to do this, this was in a previous lecture, so you can go look that up. Okay, so we're going to now do this. We're going to start with this using this as the partition function, and then we're going to take the temperature derivative of that. Okay, so E bar equals kBT squared partial T. Now we're going to put in here log Q, so that's log of, well, we'll just substitute this in, e to the negative theta over 2t divided by 1 minus e to the negative theta over t to the 3n. Okay, I can pull a 3n out, right, because this is a log, so I can just pull this out, and there's no dependence on t, so I can just pull it all the way out. So this equals 3nkt squared partial t. I'm going to do logs, and I'm going to first split this into 2 logs, so 1 log and then minus the other log here. And log of e to the negative theta over 2t, well, that's just negative theta over 2t, right? The log and the exponential cancel out. The second one, log of 1 minus e to the negative theta over t, that's fine, I can just write it like this. Plus log 1 over 1 minus e to the negative theta over t. Okay, so I've kept it in the product form. So instead of doing a minus this, I just added 1 divided by this. Okay, so this is still a plus. To go from this to the next step requires a really long chain rule step. So I'm just going to write the answer, and I hope you will forgive me. When you do the partial t, you'll get theta over 2t squared plus 1 over t squared theta over e to the theta over t minus 1. So again, if you do partial t of this, you get a really long chain rule. Long chain rule step. So I'm just going to skip it for your sake. Now notice here that t squares canceled out, right? So these t squares no longer are there, and I'm going to go to another screen. So this becomes 3n kBt times theta over 2 plus theta over e to the theta over t minus 1. All right, so CV equals partial e partial t. This is, remember, this is e bar. So this equals 3n kb theta over t squared times e to the theta over t divided by e to the theta over t minus 1 squared. And again, there's another long chain rule step. So just take my word for it. Okay, sorry, I know it's a little bit unsatisfying. All right, so that is the heat capacity of an Einstein solid. Let's see what happens when we go to high and low temperature with this model. Okay? Okay, we're back on the slides. So here's the heat capacity of the Einstein solid. What is the high temperature heat capacity? Okay, so let's put temperature goes to infinity. So if temperature goes to infinity, this term is 0, okay? And this term is e to the theta over t, so this is e to the 0, so this is 1 divided by e to the theta over infinity, so this is 1 minus 1 squared, so this is 0 squared. Okay, so I'm dividing by a 0. So I'm taking the limit of t goes to infinity, but I'm dividing by a 0. What do? Well, you got to use something called L'Hopital's rule. Did you ever think that you would hear that word again? Okay, so L'Hopital's rule, I'm not going to do it. What I'm going to do is use Wolfram alpha. Look at this. I press go. And boom! Limit t goes to infinity of this large expression equals 1. Okay? So thank you, Wolfram alpha. You don't need to be good at math when you have the internet. Okay, so this term on the right equals 1. So CV at high temperature goes to 3 nkb, which is 3R. Okay, so we reproduce the law of Dulong Petit. That's good. Yeah, great. All right, now let's go to the low temperature heat capacity. So at low temperature, this term is going to be close to 0. So this term is going to be very large, right? This is going to be a very big number. So if I plug this into here, and I'm considering this is a big number. So this is some big number squared, and let's look at this term. So this is again, this is a big number, and so if I look at the bottom here, then this is a big number minus 1. So it's still a big number, and so I have e to the theta over t basically divided by e to the theta over t squared. So this is basically going to come out to 1 over e to the negative theta, or sorry, 1 over e to the theta over t, right? Now, if I look at the full expression, so you're going to get something that looks like this. So you'll have 3 nkb theta over t squared times e to the negative theta over t. That's what we did over here. And it turns out that e to the negative x goes to 0 much faster than x squared goes to infinity. So what that means is that when theta over t becomes very large, in other words, when t goes very small, the heat capacity is going to go to 0, okay, because this term goes to 0 very fast. So that's good. Okay, so the low temperature heat capacity is 0, and if I looked at the observations from experiment earlier, the heat capacity goes to 0 at low temperature. Great. Okay, so Einstein is accurately reproducing the limiting behaviors of solids at high and low temperature, and it's kind of remarkable that we did this from essentially first principles, right? You know, we made an assumption that atoms are vibrating on a crystal lattice at a single frequency. And just from that single assumption by itself, you know, we were able to derive pretty good behavior. And so let's go and actually read what Einstein had to say in his paper. So he's talking about his previous paper. He said we had to make the assumption that the mechanism of energy transfer is such that the energy of elementary structures can only assume the values, you know, this is like h nu, okay? And then he writes, I believe that we must not content ourselves with this result. For the question arises, if the elementary structures that are assumed in the theory of energy exchange between radiation and matter cannot be perceived in terms of the current molecular kinetic theory, are we then not obliged also to modify the theory for other periodically oscillating structures considered in the molecular theory of heat? In my question, the answer is not in doubt. In other words, if energy can only exist in quantized values, then even for vibrations, we should also assume that they can only vibrate at discrete quantized values. So again, this is Einstein's genius, right? He's taking his physical insight that energy is quantized and applying it to a totally different system. Now it's vibrations of atoms on a lattice, and if you do all the math, you can reproduce this experimental observation. So, Einstein really is really is great. Okay, so let's review. So, this big red star is to let you know this is important. So the heat capacity in the Einstein temperature can be written in this form. Earlier we wrote that theta equals h nu, or h bar omega, which is another way of writing h nu. H bar omega is h over 2 pi times 2 pi nu. So this is what this is. Anyway, divided by Boltzmann's constant. And omega is what we call the spring constant. And so what the spring constant is, it's not the spring constant. It's the angular frequency. But the angular frequency is proportional to the square root of the spring constant divided by the reduced mass. And so what this means is that if I have something that has a very high spring constant, in other words, if I have something that's very, very stiff, then the Einstein temperature is going to be really high, right? If this is very stiff, and then this is going to be a high number, and this is going to be a high number. And also if it's a reduced mass is basically the, you don't have to worry about it, basically the mass of each atom, okay? And so this is, well, okay, what the reduced mass is, if I have like two atoms of different mass, then the reduced mass is like m1 plus m2 divided by m1, m2. Okay, so it's just if I have multiple atoms of different masses, this accounts for that. Anyway, okay, the point is that the lighter the atoms, or the stiffer the atoms, the higher the angular frequency. The higher the angular frequency, the higher the Einstein temperature. So let's look at some of these solids and see how we are interpreting this. Lead is a very soft material, right? And so because lead is a very soft material, it has a very low Einstein temperature, whereas on the other hand, carbon is a very light and a very stiff material, and so it has a very high angular frequency and a very high Einstein temperature. So basically, what you'll see is that a stiffer crystal gives you a higher Einstein temperature, and it will give you a smaller heat capacity at a given temperature. So carbon has a smaller heat capacity. This diamond has a smaller heat capacity at a given temperature. Here are the actual theta values for these materials. So theta for lead is 105, theta for aluminum is 428, and theta for carbon is 2230. Pretty high. When we think about entropy, remember the entropy of a solid is the integral of CV over T dt. This is what we did in the first third of the class, the classical thermodynamics section, right? So if you look at this, we're basically integrating this curve. I mean, you have this 1 over T term, but the 1 over T term exists for all these materials. So just consider that, just for now, just imagine the entropy of these materials as the area is proportional to the area under this curve, right? So lead, the area under the lead curve is a lot bigger than the area under the carbon curve, right, up to a certain temperature. So in other words, the entropy of a soft material is much larger than the entropy for a stiff material. And this is a very important physical intuition that you should try and remember. Why is the entropy of a soft material greater than the entropy of a stiff material? Basically, if I'm trying to put energy into a material, a soft material can wiggle around more. And in other words, it can accommodate more energy. I can put more energy into the vibrations of the atoms. If I have a very stiff material, I can't put that much energy into the vibrations of the atoms, and so the temperature will go up faster with a small amount of energy. In other words, it'll have a lower heat capacity, right? It will not be able to, the capacity for it to carry heat is reduced. Okay, does that make sense? I said a lot of things there. There's some logical connections. So think about this. Anything with a red star in this lecture, very important. Okay, let's move on. So if you actually measure the heat capacity of solids at low temperature, this is the heat capacity of lead, and we're at temperatures like below 25 Kelvin, okay? And so Einstein is doing pretty good up until this point, and then the Einstein curve is this dashed line, and the experimental values for the heat capacity are these red dots. And so the Einstein model starts to fail at very low temperatures if you're measuring the heat capacity. If you look at the Einstein model, remember at low temperature we expected a behavior that looked kind of like this. So we had this expectation of a scaling with this kind of scaling when you go to very low temperature. In real life, at very low temperature, the heat capacity scales with T cubed. So in this figure, this is kind of a funky figure. The x-axis is T cubed, and the y-axis is heat capacity, and we're looking below 59 Kelvin. And so what this figure is showing you is that the heat capacity is linear with T cubed. Okay? Okay, so why is the Einstein model failing at low temperatures? Well, you know, maybe we shouldn't be that surprised because the assumption in the Einstein model was kind of crazy, right? We were assuming that all the atoms vibrate at only a single frequency and have no interaction with their neighbors. But in reality, atoms aren't like that, right? Atoms in a crystal, they do not vibrate independently of one another or at a single frequency. If we look at real vibrations in a crystal, this is what's called the Debye model. So in the Debye model, we have kind of vibrational wavelengths. So here we have like what we call an acoustic wave traveling through a lattice. And if you increase the frequency of this, well, then atoms can transmit faster. And if I go to the very highest frequency, in this particular case, the atoms vibrate completely out of sync with one another. Okay? And so this is kind of a range of possible frequencies that are possible in a lattice. So if I go back to this and I start thinking about these kind of vibrations, what I'm plotting here now is like the wavelength of particular waves that I'm viewing over here. So we have very low frequency, long wavelength vibrations, right? And the lowest frequency we can have is like the length of the entire crystal, just one gigantic wave of the crystal. If I fix the boundary conditions at the end, which is that these fixed points do not move, I can start enumerating all of the possible waves, and then there is some maximum frequency that I can vibrate. This is the high frequency, short wavelength vibrations, and so there's actually a minimum wavelength, right? So this expression down here corresponds to this part right up here. So I cannot vibrate the system any more vigorously than this right here. This is the maximum amount of frequency that I can get in my system. So this is called the Debye model, and in the Einstein model's partition function, we had Q equals basically e to the negative beta n plus 1/2 h bar omega. I mean, we also had like a 3n over here. I should probably fix this on the slides. But anyway, we assumed that there is one frequency for the system, right? So there's only one value of omega. So in the Debye model, what we do is we have essentially the same expression, but now we replace omega with omega as a function of k, where omega of k is the frequency of the reciprocal vector k, and omega k equals c times k, where c is the speed of sound. Okay, hold on one second. What the hell is a reciprocal vector? What is k? What does reciprocal space look like? For those of you who have never heard of reciprocal space, it's something that you'll encounter in solid-state physics. You also see it in diffraction theory, right? A lot of times in material science, we talk about things in terms of reciprocal space, which are usually expressed in k space. And so the units of reciprocal space are 1 over angstroms, because it's the reciprocal of real space, so it's 1 over meters, or 1 over angstroms. When I was in graduate school, I had a really difficult time trying to understand reciprocal space. I think my breakthrough personally, what helped me understand it, was the idea of something like sine kx. Okay. Now, if I have a k that goes up, right, what does that mean? Well, if I think in a sine function, the higher the k, the more narrow the waves are, right? The smaller the wavelength. Okay, so I'm going to show you some applets. So this is a Wolfram demonstrations project. This is something in Mathematica that you can try. So what I'm looking at is a crystal, and what I'm going to do is I'm going to change the k values, and we're going to see how that looks like throughout the crystal. So if I have a very small kx, this corresponds to very long wavelength. Okay, think about sine with a really low value for k. Okay, so you're going to have super long wavelength modes going through your crystal. If I go higher on k, then I will increase the vibrations in this direction. And if I go really, really high, okay, so this is the highest possible k value, then you have oscillations like this. Okay, and what I can do is I can also change the polarization. So the polarization is, if I do it this way, then the crystal is doing what's called an acoustical wave. If I go like this is called a transverse wave. Sorry, this is also an acoustical wave. So this is an acoustical longitudinal wave, and this is an acoustic transverse wave. Okay, so this is going like sideways now, and you can also go sideways in the opposite direction. So okay, bottom line is, for acoustic waves, there are 3 different polarizations you can have. You can also modify the ky and kz, right? So I can do it like this. So if I change the kx, ky, and kz, it's a little hard to see, but you can now send the waves through different vectors through the crystal. Okay, it doesn't have to be parallel to one of the axes. Now I'm doing it, for example, through the 111 direction. The 111 direction is what I said. Okay. Again, it's a little bit hard to see in this GIF, but that's the concept for how k-space turns into waves through a crystal through Debye's model. So here is another Wolfram's demonstrations project, and this one is titled Phonon Dispersion Relation in the Brillouin Zone. I haven't told you what the Brillouin Zone is yet, but I'll tell it to you in a second. And so what a phonon is it's basically a heat packet. You can think of a photon being a packet of light. A phonon is what's called a quasi-particle, and it's like a packet of heat that travels through a solid. Now, there's 2 ways that phonons can exist in a solid. There's an acoustic mode and an optical mode, and we'll talk about the optical mode in a second. But the acoustic mode is similar to what we were just showing in the previous one. But what I'm plotting now is the phonon frequency versus the phonon momentum. Now remember, I'm not going to show you right now, but remember back in the Debye eigenvalues or energy values, we were using omega of k. So this is omega, and this is k. Okay, so this is k is the momentum in a solid, and omega is the frequency. Okay, so I'm going to change different k values. So I'm going to go to a very small k value. And you can see what this k value represents is like a really long and slow wavelength that goes through your solid, right? And if I start moving this up, okay, now I am putting a faster momentum. And so, when you start thinking solid state physics, you'll learn this is something called the group velocity of a crystal. And so if I go to higher k values, I'm sending heat through the crystal faster. So this is group velocity through the crystal. Until a certain point when I am at this particular momentum value, this k value, where I actually cannot port more energy into this particular mode, because this is like the most excited that this particular mode can get in this direction. Okay, and at this point, the group velocity is now actually 0, so you're actually not sending any heat or energy or information through the crystal. The optical mode is kind of similar. So notice the pattern here. So blue is going between the reds. If I go to the optical modes, it's the same idea, but it's a much higher frequency. And it's going to be hard to see, so I'm going to slow this down a little bit. And if I start going back towards zero momentum, okay, so at this point you can see that the blue and the reds are now combining like this. And if I go all the way down here, you have like perfect out of sync vibrations. So why is this called an optical mode, whereas this is called an acoustic mode? So an acoustic mode is kind of like sound, right? So what I'm doing is I'm sending sound through a material, through a solid. And so that's why it's called an acoustic wave. The optical wave is completely out of sync, and it's called optical because if I shine light on a material, the way that light interacts with a material is through optical modes. Not only optical modes, but a major form of interaction can be through optical modes. Yeah, so this is the phonon. This figure is called the phonon dispersion, and it's omega versus k, and so that's what this figure is. So what I showed in that last applet was vibrations in like one particular direction. Let's call it like the x direction, or the the lattice vector a direction. If you think about a full three-dimensional crystal, what we're starting to represent in k-space is actually something called the Brillouin zone, which exists in kx, ky, and kz space. What I'm looking at here, this is called the Brillouin zone for a cubic crystal. And this figure right here, this is a phonon dispersion plot, or a phonon band structure. Okay, you'll probably learn about this more if you take a solid-state physics course, but I still do want to talk about it a little bit in this course as well. So these phonon band structures, the way that you read this is that if you look at the Brillouin zone and you see gamma, that's a point. The gamma point is the 0, 0, 0 point in k space, and so if I look at these curves, this looks kind of similar to what I was showing you in that applet just now, right? It was like a line that goes up, and then here are the optical modes. Here's the longitudinal optical, the transverse optical, longitudinal acoustic, transverse acoustic. And what this figure is showing is if I go through gamma x, so gamma to x, and I was to plot the phonon dispersion along this direction, then I would have these curves. This would be the frequency versus the k-space. If I look at xk, so what I'm doing here is I'm looking at a line that goes from x to k, or from k to gamma, so that's k to gamma, and gamma to L, so gamma to L. These are all the different phonons in different directions in a crystal. And the reason why we're kind of looking at this very small segment of the crystal is because this segment is called the irreducible Brillouin zone. In other words, I can take this little chunk right here and use symmetry operations to fill up the entire object, right? Like I can do like a 6-fold rotation over here, so I can go boom, 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 boom. I can fill out this entire Brillouin zone over here, and I can do 4-fold rotations around here, the square, and I can fill out this thing. And so by symmetry, this is the smallest section of the Brillouin zone, and here is the phonon spectrum that shows you what are the phonon frequencies as a function of k vector in this object. Okay, so this is how you think about phonon band structures. I promise you'll see these kinds of figures in your research, and it's good to know kind of how to interpret what we're looking at here. So this is the phonon band structure for silicon carbide, 3C, which is a specific poly type of silicon carbide. What I'm about to show you next is something that I think is so freaking cool. So you all know that I'm a big fan of the Materials Project. It's a big database of DFT calculated materials properties. One of the things that you can see on the Materials Project is that for some materials, for some very common materials, they actually have the full phonon dispersion calculated for various materials. And you can click on this button here for something called interactive plots. So I'm just going to pull this up over here. So this is rutile TiO2, a very common material. I'm going to scroll down here. This is a section called phonon dispersion. And I'm going to click on interactive plots. Now, what I can do is I can actually click on different k points in the Brillouin zone, and it will correspond to what that vibration is through the crystal. So I'm just going to click on some random points, And these are the different vibrations that can go in the crystal. See, look, these are the optical modes, right? These are the optical modes of the crystal. See how they're vibrating kind of out of sync and in place. There's no transfer of information. But these are the acoustic modes. So the ones that are near the gamma point. So these are the long wavelength modes. There's one in these are all in the gamma x direction. I can click around in other directions. So these are other directions through the Brillouin zone. I can make them, just to make it clear, I can make the amplitudes really big. This is probably very unphysical. In real life, actually, atoms only move like a very small amount, like this much. Here you can even see vectors of how they're displacing. Anyway, I just think this is such a cool applet. This exists for a lot of materials. If you click around on the materials project, there's a lot of there are a lot of compounds that have this interactive toolkit, which I just love and I think is so awesome. Okay. So let's go back. This is the Debye Model partition function. And so we see here that it's e to the negative beta. Now we're summing over all the states, but now the states are omega as a function of k. And we just learned what that is. This is the frequency of the reciprocal vector k. So this is basically, this is the frequency of some vector k. And so omega of k in the Debye model only, is an approximation where omega k equals c times k, where c is the speed of sound. Okay? So remember that in statistical mechanics, sometimes it's very inconvenient to sum over all the states. If some of the states are degenerate, then it would be better to do the analysis by considering the density of states. So what the density of states is like, if I think about the Brillouin zone, like I just drew earlier, if I have let's pretend it has symmetry in the x, y, and z directions. Okay, so if I have like a vibration in the kx direction, it's symmetrically equivalent to a vibration in the ky direction or in the kz direction. So these three boxes, which I'm using to represent k vectors, these are degenerate. Okay, and so one question that you might ask is, how many states, which are vibrational quantum modes, are there within a certain frequency? Okay, so if I pick some k cutoff vector, radius of k, how many modes, how many of these little squares, which represent, n equals 1, n equals 2, n equals 3, how many of these can I have within a certain frequency or a certain radius in k-space? So let's do the derivation. So now we're going to do the derivation for the density of states, which is relevant for the Debye model. So the first step is, imagine we have what is wrong with me? A solid with plane waves. So what a plane wave is remember earlier in that Mathematica app, we had like a wave traveling as like a plane of atoms were traveling through, the sound wave was traveling through a plane of vertical atoms being pushed forward. So that's what's called a plane wave. Okay, so one way to represent plane waves is with an expression like this: u equals e to the I kx, where I is the imaginary number, k is the k vector, and x is the direction. This, if you haven't seen this before, e to the I kx, you might have seen something like this: e to the I theta equals cosine theta plus I sine theta. This is called the Euler identity. If you don't know what this is, go watch a YouTube video. It's it's a very beautiful equation. And the derivation using Taylor series is also very beautiful. But okay, so what we're going to do is we're going to say that from the boundary conditions of my solid, we're going to say that the solid has fixed boundary conditions. Okay, in other words, that the u of x equals 0, which is at one part of my crystal, is going to be equal to the u of x equals L. So this is at the other side of the crystal. If I were to plug these values into this expression, then what I have is I have 1 equals e to the I k L. Okay, that's, this is this side and this is this side. If I were to think about e to the I theta in this form, one way that you can plot this is in something called the Argand plane. And this is called the imaginary vector z, and this is the real value for z. Z is a plus bi, or some real number plus an imaginary number plus b. Okay, and so this is theta, and so we have like, as a function of theta, this equation will send you around the circle. This is a unit circle, so so cosine theta is in the x direction, and then I times sine theta, this will make it go like this, and so they'll form the unit circle. So what are the conditions where e to the ikl equals 1? And 1 is a real value that is located right here. Right, this is 1. Well, this can only happen for k equals 2 pi over L. Do you see that? If I put 2 pi over L in here, then this will be e to the I 2 pi, and so 2 pi is one circle. And if I do another 2 pi, that also works. So it's 2 pi L n, okay, for n equals 0, 1, 2, 3, all the natural numbers. All right, just to summarize what we did on this slide, we are looking at a solid with plane waves, and what I'm doing is I'm setting a boundary condition of my solid where the u on the left side is fixed and the u on the right side is fixed, and if you plug this into the plane wave equation, you'll get an expression 1 equals e to the ikl. And using this expression from complex analysis, we are trying to show that 1 equals e to the ikl. This can only be satisfied when k equals 2 pi n over L, for n are natural numbers, so 0, 1, 2, positive integers. Okay, so these are the conditions, these are the quantized values for k that we can have for our system. So in that picture earlier where we had cubes, so each cube has a volume in k space of 2 pi over L cubed. Okay, and each one of these cubes represents a quantized vibrational mode. Represents, oh my god, I cannot write. Represents a quantized vibrational mode. So the goal, when we're doing density of states calculations, our goal is to count, for density of states, we want to count the number of quantized modes within some shell of k plus dk. So just to show you what I mean, remember this was the picture that we had earlier, so we're counting the number of cubes that fall within some shell of k plus dk. Okay? And what we're doing there is we're counting the number of modes that fall, quantized modes, because modes are quantized, just like everything in nature is quantized. Certain vibrations are quantized, and so we're counting how many quantized modes are there within some k plus dk. So if I think about the volume of a shell, then this is going to be equal to 4 pi k squared dk, right? Simple things that we learned from calculus. So the number of points, number of cubes per volume of shell can be written as the volume of shell divided by the volume of points, right? That's how many points I can fit into that shell. So that would be 4 pi k squared dk, that's what we just derived up here, divided by this, 2 pi over L cubed. 2 pi cubed divided by L cubed. All right. We're going to call L cubed to be V. We're going to call this V. We'll notice that this pi cancels out. So now we're going to be left with 2 pi squared, and this is 2 cubed. So I'll just write that in there. So what does this become? This becomes, so we have 4 divided by 8. So this is going to be leaving with 2. So I'll have V. V was on the bottom previously, so now we're going to move it to the top. So V divided by 2 pi squared times k squared dk. Uh-oh, kind of cutting off on the screen there. Hope it's going to record. This is called the density of states. Very important concept in material science. Oh shoot! So you should definitely. This is a very important derivation, actually. So you should definitely write this down in your notes and remember this. It's very good. Okay, so what I'm going to write now is the density of states. So we write density of states as when we talk about phonons, we say G. So G of omega d omega equals V over 2 pi squared k squared dk, but I want it in terms of omega, okay? So I'm going to write dk d omega d omega. All right? And previously I said that omega equals ck in the Debye model. Not in real life, just in this model, okay? And so we can write that k equals omega over c. And so g of omega equals v over 2 pi squared k squared. But what I'm going to do now is I'm going to say k squared is omega over c squared. So omega over c squared dk d omega, that's k d omega. We'll just get rid of this, so this will be 1 over c. So it's going to be c cubed d omega. Okay, this is the density of states for the Debye model. All right, great. So what we're going to do is we're going to integrate the density of states, but we can't just integrate this indefinitely. We only can integrate this up to a certain cutoff frequency. Remember earlier we had a very long wavelength mode, but if I put more energy into the system and I really excite these vibrations, there is a maximum frequency that I can excite my system to, right? And so that's called the Debye frequency. And so we can constrain the density of states to say that the integral of the density of states up to the Debye frequency equals 3n. And what that is n is the number of atoms. So I can't have more vibrational modes than atoms, right? This is like the maximum amount of vibration that I can have. And so this is n in one direction. And so if I had 3n, that's 3 directions. Okay? And so I'm not going to derive what the Debye cutoff frequency is, but if you took that g of omega that I just wrote down in the previous slide and you integrated it from 0 to omega d and you solved for this equal to 3n, you would get a value for the Debye frequency to be right here. This is the value right here. And this is proportional to what we call the Debye temperature. So this is kind of like the Einstein temperature, but this is the Debye temperature. And Debye temperature, this is h bar omega d, that's this term right here, divided by kb. So here is what the density of states versus the angular momentum would look like. And remember, the density of states, this is kind of like how many of these little cubes can I fit within some radius, right? So what I'm doing here is I'm plotting frequencies. I'm not plotting k-space, I'm plotting the omega, but within some amount of frequency, how many states are there with that frequency? Okay, that's what this figure is showing. And what the dashed line is it's the result from the Debye model. So if I use the Debye model, I will have g of omega d omega equals, some constants times omega squared. And so this is a parabolic shape, and it gets cut off at the Debye frequency. So this is the maximum amount here, and this is the theta Debye temperature is proportional to what this cutoff temperature is. Okay, so the background color, this dark curve, this is what the actual density of states for a material usually looks like, and we'll talk about these. This part corresponds to the acoustic side, and this part corresponds to the optical modes. So okay, actually I'm just gonna go a few slides back to show you what I mean by this. Okay, so this is like the density of states, and if I look here, the density of states, this is density of states. Now this is being plotted in an opposite direction. Okay, so this is density of states on the y-axis and frequencies on the x-axis. When you plot it with a band structure, usually you plot this on the y-axis. You plot frequency on the y-axis and density of states on the x-axis. So frequencies is now on the y-axis, density of states is on the x-axis. And so if I look at this phonon dispersion plot, what I'm basically doing is I'm counting how many states, or basically how many blue dots you can think of, do I have at a certain frequency range. Okay, so like if I look at this figure, I have a lot of blue dots right here, basically, and I have a lot of blue dots up here, and I have nothing right here, right? There's nothing in this region, and then here at these optical modes up here, then I have some more. So this is what a real density of states might look like, and it actually has a relationship that looks kind of like the Debye model. Okay, so remember, the model is not the real result; it is just a assumption for how vibrations in solids are. Okay, so these are some takeaways. The Debye temperature is a temperature where all frequency modes are excited, and at low temperature you only have the low frequency long wavelength modes. Okay, only when you go to very, very high temperature, what you're doing is you're populating these density of states. So you're putting more and more of the energy into these high frequency modes. Okay? A stiffer crystal, just like with the Einstein temperature, a stiffer crystal results in a higher Debye temperature as well, because this is also in this expression, and a stiffer crystal will have a higher speed of sound. Okay, think about that for a second. If I have a, you can think of like a rope, right? If I have a really, really tight rope, so that the rope is very stiff, if I pluck it, it'll send that plucked vibration down that rope really quickly, right? The speed of sound will be really, really fast along that rope. If it's a really softly, if I'm not pulling the rope very tightly, then the speed of sound will be much lower. And so the same idea goes with a crystal. If I have a stiffer crystal, it's going to have a higher speed of sound. The higher speed of sound is going to result in a higher Debye temperature, and a higher Debye temperature is going to result in a lower heat capacity, like diamond, right? Diamond, very stiff, very high Debye temperature, also very high Einstein temperature, and a lower heat capacity than 3R. All right. I am not going to derive the heat capacity using pencil and paper. I'm just going to go through the derivation by slide, because the derivation is actually quite long. But anyway, so this is the energy of a, from StatMech, we know that E equals the summation of Pi EI. Of course, you all know this from now. If I do the Debye model in here, what I'm going to do is I'm going to do EI, so the energy is equal to h bar omega of, this is Q is sometimes written as K, so this is h bar omega K, okay? And the probability is just the partition function. So this is the partition function on the bottom down here. So what we're doing here is we're going to change to the number of vibrational modes times the energy of modes. And now I'm going to do a summation over this density of states. If you haven't seen this kind of notation before, sometimes people write integral d omega and they write everything else afterward. You can also think of this at the end. It's just that when you write really long things, sometimes people put d omega up here. So anyway, you integrate d omega h bar omega over the partition function, and you sum it. There's 3 polarizations, right? You get 2 transverse modes and 1 longitudinal mode. So we took that thing that we derived earlier, which was the v over 2 pi squared times omega squared over v cubed. What is this v? This is the speed of sound. So whatever I copy this from is using different constants, but this is the figure. And then again, I'm not going to derive it, but here is the average energy that you get from this expression. And if you solved it, it would look like this. And the heat capacity is the partial E partial T. And if you did that, you would get this expression. Quite complicated. But the important part is that at low temperatures, the heat capacity is proportional to T cubed. Yay! And also at high temperatures, it goes to 3R. And you're just going to have to trust me on this one. All right? So in other words, the Debye model accurately captures the heat capacity at low temperatures better than the Einstein model. If you actually plot versus experimental data, this is what you'll kind of be seeing. Okay, so the blue curve is the Einstein model. So first let me tell you the green curve is the experimental data. So we're plotting heat capacity versus temperature. So when you go to very low temperature, the green is the experimental data. Blue, Einstein, is not looking good, right? There's a big difference. And green is a Debye model. So Debye is pretty good at low temperature, but it starts to deviate a little bit at high temperature, so it's not that great. And there's another model called the Nernst-Lindemann model. The Nernst-Lindemann model is, instead of vibrating at 1 frequency, like the Einstein model said, now Nernst-Lindemann says, let's vibrate at 2 frequencies. And the 2 frequencies are corresponding to the acoustic mode and the optical mode. So this figure right here basically shows you what the assumptions are. Okay? In Einstein, everything's vibrating at a single frequency. Okay? There's a single frequency right here. It does not depend on the k vector. So this is the Einstein assumption. All atoms are vibrating independently of one another at a single frequency. Nernst-Lindemann says that it can vibrate at 2 frequencies, one around the acoustical modes and one near the optical modes, and it does pretty good. It does better than the Einstein at low temperature. And Debye says omega of k, omega is frequency, equals ck. So here's k, this is the k vector, and c is a constant, and c is the speed of sound. Okay, so this is the Debye assumption, that in k space you have this relationship between frequency and k that looks like this, where the slope of this line is proportional to the speed of sound. All right. So I'd like to conclude today's lecture by talking about how we can calculate the phonons of real materials. And what I mean by calculate is to calculate in using quantum mechanical methods, which must be run in a supercomputer. So this is like the kind of stuff that I do in my research group. We use density functional theory, and density functional theory is a quantum mechanical method to calculate phonons of real materials. And the way that we do this is that this is also an eigenvalue eigenvector problem. And the eigenvalue eigenvector problem normally is written like ax equals lambda x. So if you want to solve for this, then you can just do a minus lambda I, and you can solve for the eigenvalues. So in the phonon version, what it looks like is it looks like this, where omega is the eigenvalues. They're called the frequencies of the system. And this is the operator. This is what corresponds to A here. And this is the interatomic force constant. And so it's a matrix that has directions and ions. And over here, this is like the reduced mass of the ions. And the way that we do this calculation is you take a crystal, like so, and we do small displacements over here. And so we just take the atoms and we do some small distortions. And when you do these small distortions, what we're trying to do is we're trying to use DFT, we're trying to use quantum mechanical methods to measure the force that these distortions put on their neighboring atoms. And in doing so, we can calculate the force constant. And what I'm going to do now is I'm going to show you how we can use this to resolve this question that we had earlier. Okay, so at the beginning of the lecture, I talked about beta tin and alpha tin, and I said that beta tin has a higher entropy than alpha tin, but the question was why, right? So let's use density functional theory calculations of the phonons to try to understand the system. So if you calculate the phonon dispersion plots for alpha tin and beta tin, this is what you get. So you get frequency versus k-space from these two figures. And let's take a look at these. In alpha tin, if I think about the density of states sort of as counting dots at a certain frequency, right? There are a lot of dots in this range right over here. So there's a big peak in the density of states over here. And there's not many dots in this region, right? So you have not that many density of states in this middle region. And then you have a lot more density of states at the optical region, so the high frequency regime. On the other hand, the beta tin has kind of different. It has a lot more states in this intermediate regime. Okay, and can we rationalize this from the crystal structure? Well, remember that alpha tin has this diamond structure, right? So in this diamond structure, at low frequencies, basically there's from the symmetry, this is a high symmetry structure, and so there's only so many types of ways that these atoms can vibrate, and they're all happen to be at like this frequency right here, and there's not much in the middle. But when I go to really high temperature, I can get the optical modes, so I have new frequencies that are available at high temperature. Look at this beta tin structure. This is kind of this low symmetry floppy structure, right? And so you can imagine that if I'm putting energy into this system, there's a lot more ways I can vibrate this structure than this structure, right? So I can put all of the energy into here. You get a lot of vibrations in these intermediate frequency regimes. And what happens is that if I compare these, if I think about this as a function of temperature, when I'm at low temperature, right? Remember, the way that the temperature works is that at low temperature, when I put energy into the system, I only activate these low frequency, long wavelength modes, right? And so alpha tin can tolerate a lot more of the low temperature heat capacity. But as I go to high temperature, check this out. If I go to high temperature, I can put a lot of energy into beta tin, right? I have a lot more states, a lot more vibrational states that I can put energy into. And so what that means is that beta tin is a higher entropy structure at higher temperatures. Okay? Beta tin is a higher entropy structure. And what that means is if I look at the free energy, so this is like a Gibbs free energy of alpha tin versus beta tin, because beta tin has high entropy at higher temperature, even though alpha tin is the low enthalpy phase, at high temperature, the entropy of beta tin wins over, and there's a crossover in their free energy curves at around 310 K, which is supposedly the phase transformation temperature. Also notice this is concave, right? Like we're talking about in the geometry of thermodynamics. All right, so I hope that's very satisfying for you. We showed that from first principles calculations of phonons and from interpreting the density of states, why the Napoleon's buttons would turn to dust at low temperature, why they would turn back to alpha tin. Okay, let's do the final review. So in today's lecture, we started with a diatomic gas, and we talked about how at high temperature, you could access different degrees of freedom in your material, right? If I increase the temperature, I can store energy in rotational modes and vibrational modes. And conversely, if I reduce the temperature, I have to freeze out those degrees of freedom. And Einstein made this argument that maybe atoms can be modeled on a lattice as vibrating independently from one another, but as you go to low temperature, you're freezing out the vibrations of some of these states, right? So it's kind of like a two-state system, and the occupation of the vibrating state diminishes with temperature. And from the Einstein model, he could properly rationalize 3R at high temperature and 0R at low temperature. So this is my conclusion slides. The quantization ansatz. Ansatz is like is a guess. It's a hypothesis. The quantization ansatz is crucial to understanding the low temperature heat capacity of solids. Okay, the vibrational modes are frozen out at low temperature in the same way that vibrational modes are frozen out in the diatomic gas. Einstein assumes non-interacting, distinguishable quantum harmonic oscillators. You get 3R at high temperature, but at low temperature, you get a relationship. You expect a relationship like this, and this is not the case, right? You don't get the proper behavior. But one thing that is valuable at the Einstein temperature is that you have this very nice relationship with the spring constant and the reduced mass. And in general, if you have a stiffer crystal, this is important, okay? If you have a stiffer crystal, you'll have a higher Einstein temperature, which will result in a lower heat capacity, right? Like, okay, so just think like diamond, okay? Diamond is a stiffer crystal, high Einstein temperature. The high Einstein temperature means a lower heat capacity at a given temperature, which means lower vibrational entropy, right? Remember that curve? Remember this curve over here? So the entropy is the integral of this, right? Basically, it's the integral of this divided by T, but it's kind of like the integral of this. And so, diamond cannot sustain very much energy as a function of, cannot store very much energy, has a very low heat capacity. The Debye model is it's a modification of the Einstein model. Now atoms are not vibrating independently on a lattice. They now vibrate proportional to their k vector and the speed of sound, right? And so we derived this density of states, which had this omega squared kind of relationship. So this was the density of states for the Debye model. And it cuts off at a certain Debye frequency. And the Debye frequency was proportional to the Debye temperature. And the Debye temperature is this cutoff right here where all the frequency modes are excited. So if I was looking at this alpha 10 picture, this is the Debye temperature corresponds to when all the modes are being excited. So I've stuck all the, every single possible mode in this crystal is vibrating. Okay, in the Debye model, only low frequency, long wavelength modes matter at low temperature, and we get this T cube dependence, which is, what we wanted in the model, right? And so the same ideas correspond to the Einstein one, where you have a stiffer crystal, you get a higher speed of sound. A higher speed of sound gets you a higher Debye temperature, and a higher Debye temperature gives you a lower heat capacity. All right, so that's all for today's lecture. Here are some references for you to look through. This is what I used for the first principles calculations of tin phase transition. Is a very nice paper. If you want to read more about Albert Einstein and his role in solid state physics, then this is another very, very nice review paper. And here were the Mathematica demonstration apps that I used earlier for motion of atoms in a crystal. Okay, so thank you very much, class. I know that's the full hour and a half, but I want to talk about one more thing that I think is pretty cool if you know phonons. Just one last bit. You can leave now if this is not going to be on a test or anything. This was a really cool paper that was published a few years ago now in Nature from Northwestern University. It's called Ultra Low Thermal Conductivity and High Thermoelectric Figure of Merit in Tin Selenide Crystals. So, I don't know if anyone in our class works on thermoelectrics. For example, Professor Poudot does a lot of research in thermoelectric materials. Thermoelectric materials are materials that can convert heat into electricity. And the efficiency that they convert heat into electricity depends on something called ZT. So this is called the figure of merit. And what you want to do is you want to maximize what's called the electronic power factor. So this is like how much electricity and, well, it's called entropy, but don't worry about this part. But this is like how much energy from the electronic side does it generate. But you also want to minimize the lattice thermal conductivity. So if this is low, if the denominator is low, then ZT will be high. So in general, some good thermoelectrics have like ZT1. Before this paper, the ZT world record was 2.2, but this material, tin selenide has a ZT of 2.6, which is really, really, really high. Okay, it's a wonderful thermoelectric material. And here's the crystal structure of tin selenide. Okay, which is kind of interesting. If I think of selenium is 2- for the oxidation state, right? So for this material to exist, tin has to be 2+. But if I look on the periodic table, tin is under silicon, so you would think of it as 4+, right? So how can I have tin 2+ in this material? The extra 2 electrons are over here in what we call kind of like these floating electrons. And so these floating electrons kind of act like little electron pillows, like electron clouds in this material. And so what I'm going to do here is I'm plotting the phonon band structure of this material, and we're going to look at the different directions. So in the A direction, this is called gamma x. So if you look over here, gamma x, okay, this is the direction right here. This is the phonon frequency, and you can see that the slope is very low. And what that means is that the speed of sound in this direction is very small. And the reason why the speed of sound is so bad, the reason why the phonons in this direction are so soft is because, like I said, it comes from the electronic structure. It comes from the fact that this is tin 4+, but I have 2 floating electron clouds. And those 2 floating electron clouds act as kind of soft pillows, marshmallows that separate these layers. And like within the layers, within the gamma y and the gamma z direction, so here's gamma y and here's gamma z, you have very high frequency phonons, because these are covalently bound. But in this direction, you have very soft phonons, and that gives us this result where you have very low lattice thermal conductivity, and so you have very high ZT. Pretty cool, right? It's pretty cool. So this is how you can use all this stuff to engineer new energy materials. Okay, so thermodynamics is important. Okay, that really is the end of the lecture. So thank you very much. And this is actually the last lecture before the exam. So for the next couple uploads, I will be going through problems for exam 2. Okay? All right, thanks everyone.